Good morning, students. So, in the last class we discussed about Ampere Circular Law. What is Ampere Circular Law? The line integral of magnetic field over a closed loop is equal to mu naught times of net current flowing through the closed surface. So, now I am going to derive expression for magnetic field strength due to a straight current carrying wire. So, this question is very important for 3 marks, that is magnetic field due to a straight current carrying conductor. Okay. So, I am going to derive the expression for magnetic field due to a current carrying conductor by applying Ampere's circular law. So, let us take first a current carrying conductor. So, assume that this is a conductor carrying a current of I. Okay. Now, as we know, we can apply Fleming's right hand rule. If a current carrying conductor is hold like this, so this is current carrying conductor, then the magnetic field will be in the form of circular loop. So, let us draw a circular loop concentric to current carrying conductor. Let us assume that the radius of this loop is R. Now, what is the magnetic field? The magnetic field is obtained by drawing a tangent at any part of the circular loop, right? So, to the plane of the circle, if you draw a tangent, then it gives what? The magnetic field. So, this is the magnetic field direction. So, we should apply Ampere Circular Law or Bird's law. We should consider a small current element, right? So, this is the small current element, this is dl. So, dl is also along the same direction. Now, here both B and dl are along same direction. So, that is the concept what we know, right? Yes. Applying Ampere Circular Law. What is Ampere Circular Law? Line integral of magnetic field over a closed loop is equal to mu naught times of net current flowing through the loop. Have you observed here magnetic field and length of the element both are along same direction. So, I can write this as integration of B dl cos 0 is equals to mu naught I, because the current that is flowing through the conductor is I. So, net current is I. That implies cos 0 is 1, magnetic field is B into integration of dl is equals to how much? Mu naught I. Integration of dl is L. What is the length of the loop? This circular loop is circumference. So, it becomes B into 2 pi r is equals to mu naught I. Finally, what we want? B, that is magnetic field, is equals to what? Mu naught I by 2 pi r. So, this is the magnetic field due to a current carrying conductor. So, what we consider ma? Here we consider a current carrying conductor that carrying current of I. As we know that if it is carrying current in a straight conductor, then the magnetic field will be in the form of circular loops. We draw one such circular loop of radius. How to get the magnetic field direction? If you draw tangent at any part of the circle, it gives the direction of magnetic field. To find the magnetic field, we should take a current element. Here we are taking a small current element dl. Here B and dl both along same direction. So, now we come to this is a closed surface. So, we can apply Ampere Circular Law. What is Ampere Circular Law? The line integral of magnetic field over a closed loop is equal to mu naught times of net current flowing through the surface. Here B and dl are along same direction. So, line integral of B dl cos 0 is equals to mu naught I. Cos 0 is 1. So, B into integration of dl is equals to mu naught I. Integration of dl is L, nothing but length of this loop. What is the length of the loop? 2 pi r. So, B into 2 pi r is equals to mu naught I. B equals to mu naught I by 2 pi r. This is the magnetic field due to a current carrying conductor. Next one. magnetic force on a current carrying conductor. So, we should not confuse here force on a charge. The force on a charge, moving charge, only one charge is what? QVB sin theta. Force on a charge is what ma? QVB sin theta. So, here we are going to calculate magnetic force on a current carrying conductor, not on a charge. Already on a charge we know that F is equals to QVB sin theta. So, you should not confuse here, right? Okay, let us take a conductor. Okay, so this is a conductor having length L. Now, here in this conductor, generally take that if you apply some electric field, the electrons are moving in this direction. So, what happens? Take only one electron first. So, the electrons are moving in this direction with some drift velocity d. So, these are the electrons. Now, electron is moving from this end to this end. So, the current starts to flow this end. So, this is the current direction. Now, let us take the magnetic field. This is magnetic field which is pointing outwards. So, if you take one electron here, so one electron on one, it is making what angle? Theta. Or with the direction of motion of electron, it is making an angle what ma? Theta. So, this is the representation, means we consider a conductor having length L. In this, electrons are moving from this end to this end. So, the current starts to flow in opposite direction. So, if you apply magnetic field at an angle with respect to theta, the force on a charge, first we will consider on a charge in magnetic field making an angle theta. So, what is the force on each charge? Let us assume that F dash is equals to QVB sin theta. Here the charges are moving with what velocity? Drift velocity Vd. So, what is the charge moving here? Electron. So, EVD B sin theta. This is the force on one charge. Let us consider N charges per unit volume. So, in this conductor, how many charges are there? Per unit volume, N charges. For a volume V, how many charges will be there? N is equals to N, or N dash is equals to N into V, right? What is N? Number of charges per unit volume into total volume is what? NAL. Okay. So, how many number of charges are there here? N into AL. Total charge Q is equals to what? NEAL. Okay. Now, how many charges are present here? These many charges are present. So, this number of charges are present. On one charge, this is the force. The total force, or you can say that the number of charges present in length of the conductor, you can say that, no problem. The total force on the free electrons on the length of the conductor is the total force on free electrons of the length of the conductor is how much? F is equals to N into F dash. How many electrons are present in this one? How many? NAL So NAL into what is the force on each charge? EVD B sin theta. So rewriting this equation as F is equals to NEAVD LB sin theta. ಬರೆಯುವುದಮ್ಮ? Can write na? NEAVD LB sin theta. We know very well that the relation between current and drift velocity is NEAVD. So F is equals to, instead of NEAVD, what we can write? ILB sin theta. So the force acting on a charged current carrying conductor is how much? F is equals to ILB sin theta. This can also be written as what? Here I is vector scalar quantity, so we cannot write in vector form. F is equals to I into L bar cross B bar. I into L bar cross B bar. If a conductor is placed along the direction of magnetic field, means if you place the conductor along the direction of magnetic field, then theta is equals to 0, it experiences no force. It experiences maximum force when? It experiences maximum force when conductor is placed how? Normal to magnetic field. When the conductor is placed normal to magnetic field, it experiences maximum force because theta is equals to 90, F is equals to ILB. So the force on a charged conductor is ILB sin theta, whereas charge is QVB sin theta. So these two formulas are very important. Now what we are going to derive the relation? Two derivations. We are going to derive one derivation that is very easy and very important for 5 marks. That is expression for force between two parallel straight conductors carrying current. Expression for force between two parallel straight conductors carrying current. See here, according to the question, what we should consider? We should consider two conductors which are parallel and straight and infinite conductors. Assume that both conductors are carrying different currents. What are the conductors carrying current? I1 and I2. Let us give the names of these two conductors, that is X and Y, separated by a distance of D. So we consider two conductors carrying different currents. What are the currents carrying here? I1 and I2. Name of these conductors what? X and Y, separated by distance D. Okay. Now here, this is a current carrying conductor individually. This is a current carrying conductor, right? So this is a current carrying conductor. It produces magnetic field, right? So it produces magnetic field. So this is what? A current carrying conductor. Because of this current carrying conductor, it produces magnetic field. So let us assume that a point P here. So at this point P, what is the magnetic field is? B1. Let's assume that this is B1. So this current is carrying conductor, right? So it produces inward magnetic field. It produces what? Inward magnetic field into the plane. So this is a current carrying conductor. Because of this current conductor, magnetic field at P is B1. So magnetic field B1 due to current carrying conductor X. What is the magnetic field due to this one? B1 is equals to, we already proved, magnetic field due to infinite conductor is what? Mu naught I1 by distance is what, ma? 2 pi r. Because the current carrying is I1, so mu naught I by 2 pi r. What is the current carrying here? I1 by 2 pi r. Okay. So this is a current carrying conductor, produces magnetic field at P. Now this conductor is under the magnetic field of this one, right? So this exerts force on this one. What is the direction of force? This one. This is F1. So force on conductor Y due to B1, because it produces magnetic field and exerts force on Y. So what is the force? Now only we did it, right? F is equals to ILB sin theta. F is equals to what, ma? ILB sin theta. So on which conductor we are exerting force? Y. So Fy is equals to, what is the current carrying this conductor? I2 into LB sin theta, right? So I2 into L, what is B1? Mu naught I1 by 2 pi r, theta here perpendicular, right? Sin 90. So force on Y due to B1 is what? Mu1 I1 I2 by 2 pi r into L. This is the equation number 1. Now see, this is also a current carrying conductor. It also produces magnetic field at point Q, and this is inwards, this will be outwards. So what is the magnetic field here? B2. So we can write the same thing, right? What? B2 due to current carrying conductor Y. So what is the magnetic field to this one, ma? B2 is equals to mu naught I2 by 2 pi r. Now this magnetic field exert force on X, right? That is F2. So we can write F2 as, or this is, you can don't confuse that here. This is Fx and this is Fy. So what you can write here? Force on X, force on X due to B2. What is the force on a current carrying conductor, ma? F is equals to ILB sin theta. It is exerting force on X, so the current carrying in X I1, L, magnetic field is B2. So force on which one? X. So Fx is equals to I1 into L. B2 is what? Mu naught I2 by 2 pi r into sin 90. So what do you get? Fx is equals to mu naught I1 I2 by 2 pi r into L. So what you observe here? The force exerted by Y is mu naught I1 I2 by 2 pi r into L. In the same way, the force exerted due to X is equal to what? Mu naught I1 I2 by 2 pi r into L. So from this, what you can say that from 1 and 2, Fx is equals to Fy is equals to L. Therefore, F is equals to mu naught I1 I2 by 2 pi r into L, or force per unit length is equals to what? F by L is equals to mu naught I1 I2 by 2 pi r. So, this is the expression for force between two current carrying conductors. Here we have to define the definition of 1 ampere. This is the basic and fundamental definition that has been derived for 1 ampere. So, you should get 1 ampere means what we have to do here? I1 is equals to I2 is equals to 1 ampere. When here substitute that, if the distance is 1 meter, then what is F by L? F by L, mu naught value how much? 4 pi into 10 raised to minus 7 by 2 pi. I1 and I2 are 1 and 1, by distance is 1 meter, 2 pi 1s are 2 pi 2s are. So, what do you get? 2 into 10 raised to minus 7 Newton per meter. So, we can define the definition here as, you only define, how to define the current carrying in a conductor in these two conductors is said to be 1 ampere. When two parallel conductors carrying current separated by distance of 1 meter experiences a force of 2 into 10 raised to minus 7 Newton per meter. So, I will define the definition as, it is the current, ampere is the current, or you can write ampere is the current which when flows through two infinitely long straight parallel conductors separated by distance of 1 meter in free space experiences a force of attraction or repulsion of 2 into 10 raised to minus 7 Newton per meter. So, this is the definition. It is the current with which when flows through two infinitely long straight parallel conductors separated by distance of 1 meter in free space experiences a force of attraction or repulsion of 2 into 10 raised to minus 7 Newton per meter. This question is very important for 5 marks. I said now in this chapter we have 2 questions, that is magnetic field in a circular loop along its axial line or force between two conductors, 5 marks. So, if 10 times, if they ask 6 to 7 times that question, remaining times this only I have as the question. So, this question is very simple See here, I am just revising the concept. We consider two conductors I1 and I2 carrying currents having conductors names X and Y. So, we already derived magnetic field is a straight conductor carrying current. So, at a point P, if you take a point P here, it produces magnetic field, right? So, what is the magnetic field produced by this one is B1. So, this conductor carrying current and produces magnetic field. What is the magnetic field produced by this one? B1 is equals to mu naught I1 by 2 pi r. Since this is a current carrying conductor and produces magnetic field, this conductor experiences the force because this magnetic field is perpendicular. What is the force on Y? Force on Y is equals to ILB sin theta. I is current carrying conductor, I2 L mu naught I1 by 2 pi r sin 90. So, now this is also a current carrying conductor. Yes, it also produces magnetic field. What is magnetic field produced by this one? Bu2 is equals to mu naught I2 by 2 pi r. It also exerts force on conductor X, that is Fx is equals to mu naught I1 I2 by 2 pi r into L. So both are exerting same forces. So we should represent the direction of magnetic fields here. One is outwards, one is inwards. Now this exerts force on this one. This is Fx and this is Fy. Both are same, that is equals to mu naught I1 I2 by 2 pi r into L. Here we should remember one more point that is very important one. Here when two conductors carry same currents, the force between them is, till now in physics we learned like charges, like forces will repel. Between them is what? Attractive. Here it comes in reverse, because both are producing magnetic field, one out of the plane, one into the plane. So they attract each other. When two conductors carry same current, the force between them is attractive. And the second one, when two conductors carry opposite currents, the force between them is what it comes? Repulsive. Okay. So today class we learned three derivations. One, magnetic field with a straight conductor by using Ampere Circular Law, that we got D equals to mu naught I by 2 pi r, and force on a charged conductor. Force on a charged conductor is ILB sin theta, force on a charge is QVB sin theta, and we have calculated force between two current carrying conductors. So these questions are very important. Here in this class what I discussed is one question for 5 marks, another question for 3 marks. Thank you.